part, which is really about the question, how does conscious visibility emerge in the brain? There are multiple ways of studying visibility, and sort of a very pure way of doing it is to look at the effects of just having low sensory input, for example. You can do that by reducing the contrast level. There's another technique that has been studied a lot, which is called visual masking. And the nice thing about visual masking is that you can, for example, present a target stimulus, like a letter, and you present a mask. And what really determines the visibility of this target is the timing between the target and the mask. So in some way, it's really, and you can also reverse the order, so you can sort of make sure that your the physical stimulus strength is sort of similar, and what just matters is the timing. And this is what I would call sort of threshold paradigms. And then there are the paradigms that deal with perceptual suppression. So the most famous one is probably the binocular rivalry. Binocular rivalry consists of presenting two different stimuli to the two eyes. So left eye sees, for example, a face. The right eye sees a grating, and then your perception would just switch from one perception to the other. So it goes then from a grating to a face. And one stimulus that has been developed by now, that has been extensively used now, is probably the most used suppression paradigm we have right now. It's called continuous flash suppression. It is sort of a continuous way of inducing binocular rivalry, but the really nice thing is that when the contrast level is not too high of the stimulus that's shown to one eye, and you present like this sort of flickering mask and quickly changing mask in the other eye, then you can continuously, as the name says, suppress, for example, the face. And you can do that for a really long time. So you can make sure that like the face never enters your consciousness. And the emotion-induced blindness, we have seen yesterday already from now, is sort of a related phenomenon. But those are sort of suppression paradigms where you have a sort of salient stimulus that is perceptually suppressed. And I'm pointing out the difference because the neuronal correlates are a little different for the two types. So in one case, we have just low threshold stimuli and need to detect them. In the other case, it seems to be that the visual system realizes that something is strange, incoherent, and then actively suppresses it. It's sometimes intermingled in the literature, but next time you come across some visibility paradigm, I sort of want you to think about whether it was threshold or perceptual suppression. So this part of the lecture is going to be a little bit more hardcore. So please interrupt me if you if it's just too complicated, or I feel I still want to show you how vision works before we get to the disorders. So for vision, you need some sort of physical stimulus, right? That's photons emitted by light, by the objects reflected, by the light reflected from the objects. And those photons, they hit the retina. They are then changed into an electrical signal, which is going along the nerve. And then go to the first station in the thalamus. It's called the lateral geniculate nucleus. And then the signal is transmitted to the primary visual cortex. And from there, it's in the visual cortex. Signal is just okay. It's transmitted through a huge amount of different visual areas. So the monkey has about 40. There are still visual areas adding. The human probably has even more. So it's a sort of a complex system, and somehow perception is supposed to arise in the interaction, or from the interaction between all those visual areas. If you have a stimulus like this, for example, a relatively complex pattern, then, and you record neuronal activity in the visual cortex, you put an electrode in the visual cortex of a monkey. Interestingly, most of those experiments have been done in anesthetized monkeys. So the basis we know of the visual processing was, in earlier days, Jubel and Wiesel was all anesthetized monkeys. So apparently you don't need consciousness for getting those visual properties. So cells in the primary visual cortex, so the first cortical station of visual processing, respond to very simple features like orientation of lines. They have very small receptive fields. Do you know what a receptive field is? I have to explain it? No. Yeah. Just they have a very small region in space they respond to. Then at the higher level of the hierarchy, for example, this would be area before, already responds to stimulus combinations, more complex patterns, for example. And as you go then more towards the anterior part or in front of the brain in the so-called Inferotemporal Cortex, you have neurons that are already responsive just for a certain combination of colors and forms. And as you go even more anterior, you have basically you have cells that are just responding to a certain phase, for example. So they're super specific. And also in this part of the cortex in humans, there have been studies in epileptic patients where they also sometimes need to put electrodes to see where the epilepsy comes from. They also reported conceptual neurons there. So there is this famous Jennifer Aniston neuron, which also responded to just the sound of Jennifer Aniston, for example, and just the word. And yeah. So the question is, yeah. So is percept then arising sort of as the stimulus is processed through the visual hierarchy or not? And in fact, just in terms of the basic visual processing, the problem is, yeah.
Well, is it in the early stage of like this image processing? Is it just like a layered feed-forward network or something like that?
I have drawn it as a feed-forward network. I will show you in a second. It's obviously, yes. So I have drawn it in the feed-forward, but obviously there is always back connection. So the feedback connections, they are very numerous. So, and interestingly, the problem, how those features are integrated then in the inferotemporal lobe is completely unresolved. So it clearly does not work the way you may think intuitively, that just this little details are assembled together and then they are put together and then it comes out here as a whole, right? So this is a computational problem, even like without any consciousness question, is completely unresolved. Yeah. And in real, and this is not even real, but the scheme looks like this. So this is the famous Van Essen scheme. So here are now also the back connections. So all those areas are projecting, they are communicating with each other, projecting forth and back. And so this is, yeah, and this is even a super simplified circuit, but this is sort of the task we are standing in front when we are talking about how visual awareness, for example, arises, because it's somewhere it must come out of here. And I mean, now say we look for the neuronal correlate of consciousness, what are we actually looking for? And there is this definition from Christoph Koch and Quick, which is that this should be the minimal neural mechanisms that are sufficient for any one conscious percept under constant background conditions. And this is the notion I would like to discuss with you later. And then the question becomes, when can we actually be sure that we have found it? And they are stating in their last review, Koch and Tononi review, I think you had it on your lists as well, they say stimulating the relevant neuronal populations via non-invasive methods, for example, TMS, TDCS, decide, or invasive microstimulation will give rise to a specific percept or disable it. And that's the first question I would like to discuss with you then probably in the session later, is what does it actually mean, jointly sufficient? What sort of meaning does it have in a reciprocally connected network? And what is the type of experimental evidence that would actually convince you that we have found the neuronal correlate of consciousness?
Is it right to understand that you've changed the meaning of NCC from the first talk, or the first part of the talk in the morning, to this talk? Because I think in the first talk you talked about these like patients in vegetative state, and And I think you talked about they're having awareness and stuff, but I suppose they don't have percepts. And so if we talk about neural correlates of consciousness in their case, I think it's different from this one. So
I'm talking, yes, okay. So in the first talk, I was talking about the prerequisites and the general awareness. And now we switch to talking about content. So we can still discuss whether, as we have started already yesterday, whether it's possible to have a general awareness without actually having a content. But I'm now make it easy for myself and just pretend that those are completely different things. So let's just assume the general, definitely the person is awake and the person is generally aware also of him or herself. And now we switch to the question, what is the correlate of the content? With disclaimers that would come with that.
Could you expand on the second question?
This is a question I actually don't know the answer to. That's why I would like.
The second one.
The second. Yeah. Okay, what does sufficient? So this is really the official definition of visual consciousness, when like the neuronal correlate of consciousness. This is supposed to be the jointly sufficient neuronal population, neuronal activity that would give rise to consciousness. And I sort of started to ask myself, I also have discussed it yesterday with now, what does it actually mean sufficient? So what are we looking for?
Maybe you can go back to the definition of this is here. One.
Minimal.
What does this, is this definition, good enough, or does it actually make sense to you? That's the
yeah, sorry, I think we both realized that sort of this is the mantra of the neuronal correlate of consciousness. You would always bring this as a definition. And then the moment you sit down and you try to convert it to some sort of experiment that would make sense at the end, you realize, so what, is this actually a good definition? Is that really what we are searching for? It's more an open question that I would really like to discuss. So there would be an easy answer to that. I just would like,
That's the word that kind of threw me off a little bit with the use of the word jointly.
They say, in the review, they say, yes, they say jointly.
Like in your in the actual question, jointly.
Yes. The jointly is actually belonging here.
Right.
Yes. Right. Yes, the jointly was not in the original definition. In the new review, they say jointly, and that sort of changes the game a little bit. Yeah.
Can you see the number 3 again? I'm trying to write them down.
Maybe I should. Okay, yes. So what would be the
practical thing? Shall I collect your emails, your questions, and email that to?
That would be great. I could also just give you the slides with the questions, and then you can
write them down and send them. Can you go back to question 1?
Oh. Okay, so, what is the correct spatial temporal scale? Because that would also determine the technique that we actually use to look for the neuronal correlate of consciousness.
Yeah, thank you.
Okay, and now this part I can now do only exemplary. But it's the question, so how you study the neuronal correlate of consciousness. And we try in the laboratory to reduce the problem. So we just say, okay, you have a red dot, for example, or a grating or a face, and the thing is visible, this object is visible or it's invisible. And we use a suppression paradigm in the laboratory for more or less practical reasons that we have come up with previously, which is sort of a combination of binocular rivalry and emotion-induced blindness. And the nice thing about this paradigm is that when you turn the target on, you see it for a while, let's say 2 seconds, and then you turn a surrounding dot pattern on. And this is the moment when this red dot is subjectively disappearing or not disappearing. And this is nice for electrophysiology because there is no spatial overlap between what we would call a target that is going to disappear and the surrounding pattern. So that's better because then you have a cell that's really responding to this and not to the surround. And it can be also parametrically varied very nicely. And it also, by playing tricks with the eyes, for example, if the surround is shown to the same eye as the target, it's not perceptually getting suppressed. So those are the sort of catch trials we use because we need to have a condition when we do monkey physiology we can train the monkey with. And the monkey, if he can cheat and can have an easy way out, he will. So whatever we use as catch conditions really need to look alike as our experimental conditions that we then call a no-catch condition or a condition where we simply don't know anymore what the percept is going to be so that we can turn that ambiguous. And this is about how it looks. So of course much bigger. So yeah, so this is about how the full stimulus looks like. That's what we use. It's sort of complicated to train a monkey on this. So because you need to also account for all the eventualities. Like, do you have to train the monkey that he should only release the lever, for example, if the target really completely disappeared, like that. And so what he needs to do, and he needs to fixate for a long time, and that takes time. So we are really looking at 1.5 years until the monkey is actually ready to perform the first experiment. So that's way more complicated than you would have that in a human experiment. And I show you just a couple of examples of the neural correlates of the perceptual suppression, or when the target became invisible like this. So the monkey is sitting there, he pulls the lever when he sees the red dot, for example, and he releases the lever when the target becomes perceptually suppressed. I'm showing you the ambiguous conditions. So those are the conditions where we simply cannot tell what the monkey is seeing. So the monkey really needs to tell us. And this is area V1 now, again, the primary visual cortex. And if you look at the neurons there, you see that when the monkey was reporting that the target became invisible versus visible, those lines are completely overlapping. This is the period where the monkey reported that the target had disappeared. And this is the physical removal, just to make sure that the set is actually responding to the physical removal. And you see, like in area V1, there was just a very small subportion of the cells who did anything, and if they did, it was very small, what we would call a perceptual modulation. And then as you go a little higher in the hierarchy, for example, area V4, you see that now the cells, they do start discriminating between visible versus invisible.
So that one actually responds more when monkey reported the invisibility.
Yeah, exactly. This is also why I think this is the perceptual suppression, at least like with binocular rivalry or with this paradigm, is a really active process. In the pulvinar, it was in the thalamus, it was the same thing. So the target disappears, and then you actually get an increase in neuronal activity. So this is already strange. So half of the cells go this way in V4, and half the cells the other way. In V4, actually, there are more cells which are decreasing their activity, but pulvinar, it was really 90% of the cells which increase their firing when the target perceptual disappears. But the same would be for the physical removal. So they usually go together. So your perceptual suppression activity is really correlated with the activity that you get for the physical removal too. And the whole thing also gets a little bit more complicated because, of course, we had designed the experiment so that the surrounding dots are not activating the cells, but that basically rarely happens. So you can move like 5 degrees outside of the classical receptor field in V1, and you would still get, with this huge moving surround, you would still get a huge amount of activity. It's just delayed and whatever, but it's really difficult to get a perceptual condition to basically get perceptual suppression if you would not activate a given V1 cell with the surrounding pattern. That probably is also telling something, I guess.